All right, let's get right to it. We have the strategic technical outlook for the 2024 to 2026 cycle on the desk today.
We do.
And for this deep dive, we're doing something a little different. The mission is pretty straightforward. We are stepping into the shoes of senior strategy consultants at a top-tier global firm.
Right. And our client, well, our client is you, the listener. We're assuming you're the R&D director, maybe the chief engineer at a major automotive OEM.
Exactly. And to be blunt, we aren't here to hold hands. We are here to deliver the technical strategy report that your board has been asking for.
Precisely. And the directive from that board is, it's really clear. The status quo is just bleeding money. So we've analyzed the data. We've talked to the key industry players, AVL, VI grade, AB Dynamics, HMS, Element,
Great ones.
the ones who are actually in the trenches. And we've applied a pretty rigid McKinsey-style analysis to all of it.
Okay, so what does that mean in practice?
It means we're going top down. We start with the big picture and drill down.
Yeah.
And we're keeping this MECE.
MECE. That's mutually exclusive, collectively exhaustive.
You got it. The idea is we need to cover the entire engineering landscape, from concept to factory floor, without a lot of overlap, and more importantly, without missing the critical gaps, because that's where the money is disappearing.
And the context for this whole report is, frankly, brutal. We're looking at a global warranty bill. Get this. It hit roughly $450 billion in 2022.
It's a staggering number.
That is not a typo. $450 billion. I mean, if you are an R&D director, that number is basically your report card.
And it's a failing grade. It says the complexity is outrunning your processes.
At the exact same time, the market is just screaming for speed.
It is. It's what we call the compression of the V cycle.
Yeah.
Historically, you had, 60 months to develop a new platform?
Yeah, 5 years. You had time to fail, fix it, retest.
You had a breathing room.
Today,
if you aren't hitting starter production, SOP, in 24 months, and frankly 18 months if you're trying to compete with the new players coming out of the East,
then you're launching a car that's already obsolete. The tech has moved on.
you're launching obsolete hardware. So the core conflict, the impossible equation we are solving for you today is this. How do we cut that development time by 60% while simultaneously reducing that $450 billion warranty bill?
It just sounds paradoxical. Faster usually means riskier. It means more mistakes, not fewer.
In the old paradigm, yes. In the hardware-driven world, absolutely.
Yeah.
If your strategy is build physical prototypes faster, you're just going to break more things and spend more money.
Okay, so the strategy has to change.
It has to shift. The strategy we're outlining today shifts the burden from the physical to the virtual, and from a linear sequential process to a parallel one. So to keep it MECE, we have structured this entire report into 3 core pillars.
Lay them out for us.
Pillar 1 is architecture and market strategy, the foundation. Pillar 2 is virtualization and calibration. That's the whole shift left philosophy in action. And Pillar 3 is physical automation and the digital loop, how you connect it all back together.
Got it. Okay, let's open up Pillar 1 then, the strategic landscape. When we look at the global map for the next couple of years, 2024 to 2026, what do we see? Are we looking at a unified global standard, one set of rules for everyone?
Not even close. We're seeing what we call a double reality, a fundamental bifurcation of the market. It's 2 different worlds.
How so?
Well, if you are an engineer or an engineering director and your target is the Asian market, specifically China, you are operating under the umbrella of the 15th five-year plan.
Okay.
And the mandate there is crystal clear: technological sovereignty and speed. It's about national strategy. They're very explicitly moving from being a follower to being a standard setter.
When you say standard setter, you mean they're not just building to spec, they're writing the spec for things like autonomous electric vehicles, AEVs?
Exactly. They aren't waiting for ISO or SAE to spend 5 years forming a committee. They are defining the protocols, the safety standards, the data formats right now. And they are executing with what everyone was calling China speed.
I've heard that term. What does it mean in practice?
It means we are seeing real-world development cycles of 18 months, start to finish, that is. That is barely enough time for a legacy OEM to freeze the clay model of a car, let alone validate the entire powertrain and software stack.
That puts just immense pressure on the Western OEMs. I mean, if you're sitting in an office in Detroit or Stuttgart or Munich, you can't just ignore that pace. But the market reality over here is different, right? We're seeing a bit of a cooling off on pure EV adoption.
That's the other side of the double reality.
Yeah.
Correct. In North America and Europe, the primary pressures aren't just speed, they're affordability and regulation. The mainstream consumer isn't biting on these, $60,000 EVs at the rate that the forecast predicted 2 years ago.
So what's the strategic move?
For the 2024 to 2026 window, the pragmatic strategic pivot we're seeing is actually a step back, or maybe a step sideways, toward hybrids and extended range EVs, the ERVs.
Which, from the chief engineer's perspective, is a total nightmare.
It's a resource nightmare because now you have to maintain your legacy ICE, your internal combustion engine assets, you have to develop entirely new hybrid powertrains, and you have to keep pushing your pure EV platforms forward so you aren't completely left behind in 2030. You have to do everything all at once.
Wow. Okay, so where's the common thread? What's the one thing you have to get right no matter what's turning the wheels?
Here is the single most critical insight of this whole section. Regardless of whether the propulsive force comes from a lithium-ion battery or a gasoline engine, the profit pool has shifted. It's gone. It has moved entirely from the hardware to the software and the data.
So even if you're building a hybrid?
Even if you are building a hybrid, if it is not a software-defined vehicle at its core, it is a dinosaur.
Yeah.
It's a fossil the day it rolls off the line.
And that brings us right to the foundation of the modern vehicle then. Zonal architecture. We've all heard the buzzword. But let's get technical for our listener. Why is this the absolute hill to die on for 2026?
Because the legacy approach, what we call distributed architecture, has hit a hard physical limit, a brick wall.
What do you mean by that?
I mean, for the last 30 years, when we wanted to add a new feature, say a blind spot radar, what did we do? We added a dedicated ECU, a little black box, and we added a dedicated wiring harness that ran from that box to the sensor.
And we did that for everything. Power windows, heated seats, every single sensor.
For hundreds of things. We are now carrying literal kilometers of copper wire in a premium vehicle. It adds incredible weight, which kills EV range and creates this spaghetti monster under the dashboard that is impossible to update, impossible to diagnose, and a massive source of those warranty claims.
So zonal architecture is the cleanup crew.
It's a total rezoning. It's a philosophical shift. You stop grouping by function like all the door locks report to one central locking module. You stop that and you start grouping by geography, by physical location.
Okay, so you have a front left zone controller.
Exactly. And that one box, that zone controller, it handles everything in that physical corner of the car. It runs the headlight, it reads the left wheel speed sensor, it controls the cooling fan motor, and it flashes the left turn signal. It's just a generic input-output handler.
But that zone controller isn't making the big decisions, right? It's not deciding when to turn on the cooling fan, it's just taking orders.
Correct. It is a dumb soldier. It's a powerful but obedient soldier. The general is the central HPC, the high-performance computer. All the complex logic, all the intelligence is centralized into one or maybe two powerful brains.
And the benefit there is massive.
The immediate benefit is you reduce that wiring harness weight by roughly 20%. That's
good.
Huge for an EV.
Yeah.
But, and here is the massive risk for our listener, for you as the R&D director.
Yeah.
It introduces an absolutely massive software complexity challenge.
The famous freedom from interference problem.
You've got it. This is the ISO 26262 nightmare scenario. If you put your infotainment system, which is a quality managed or QM software component.
Something not safety critical.
Right. And you put it on the same high-performance silicon chip as your autonomous emergency braking system, which is ACE-LD, the highest safety level. You have to be able to mathematically prove that when the driver's music app crashes, it cannot, under any circumstances, crash the brakes.
How do you actually solve that? I mean, is it just about writing better code, more testing?
No. You can't test your way out of a bad architecture. It has to be solved at the architectural level.
Yeah.
You need robust hypervisors. You need hardware-enforced memory isolation. It's about partitioning the CPU cores so that the safety-critical functions have guaranteed bandwidth and guaranteed memory access, no matter what the non-safety cores are doing.
So it's a systems architecture problem.
It is. And if you don't have a systems architect on your team who understands hypervisor configurations at a kernel level, you are heading for a multi-million-dollar recall. Period.
Okay, that's the brain. Let's talk about the propulsion side of the architecture. The industry seems to have coalesced around 800-volt systems as the target. But is the supply chain actually ready for mass adoption in this 2024-2026 window?
That's a great question. The voltage itself is ready. The standards are there. The bottleneck is the silicon. It's the power electronics. We are in the middle of a huge, painful transition from the old silicon IGBT's insulated gate bipolar transistors to the new world of wide bandgap semiconductors, specifically silicon carbide or SiC.
And the benefit of sync is all about efficiency.
All about efficiency. The switching losses are much, much lower. You're looking at a 7 to 10% range increase just from upgrading the inverter from IGBT to Senken. That's free range. You didn't add the single pound to the battery. But Senken is notoriously expensive and hard to manufacture.
Right, I've read about the yield issues. Silicon carbide as a crystal is incredibly hard and brittle. It's difficult to grow large, defect-free wafers.
It has been. But that's where the 2026 breakthrough really lies. We are tracking the industry's shift from 200 millimeter wafers, which is about 8 inches, to 300 millimeter wafers, or 12 inches.
And that doesn't sound like a huge jump, but in terms of area,
It's simple geometry, right? A 300 millimeter wafer yields roughly 2.3 times more chips than a 200 millimeter one. It's a massive leap in scale. And that increase in volume is what finally pushes the cost of silicon carbide down to a point where it can go into a mid-market SUV, not just a $150,000 Porsche Taycan.
okay, so the hardware is getting there, but there's an infrastructure problem, isn't there? If I drive my shiny new 800-volt architecture car to a 400-volt charging station, which is still most of them, I can't just plug it in. The physics doesn't work.
No, you need a boost converter. You have to step up the voltage. And this presents a really interesting strategic decision for you, the chief engineer. There are a few ways to do this.
What are the options?
Option one is the brute force approach. You add a dedicated DC to DC converter box somewhere in the car. It works. But that box is heavy, it creates heat, it takes up space, and it adds, say, $500 to your bill of materials.
Not ideal. What's option two?
Option two is what's called battery switching. It's clever. You use a series of high-voltage contactors, or switches, to physically reconfigure the battery pack. When you're driving, the pack is wired in series for 800 volts. When you plug into a 400-volt charger, you throw the switches and reconfigure it as two 400-volt packs wired in parallel.
That's pretty smart, but what's the catch?
The catch is that high-voltage contactors are mechanical devices. They have moving parts. They can wear out. They can get welded shut. They are known failure points. So the really elegant solution, the one we're seeing gain major traction for 2026, is the traction integrated booster.
Okay, break that down for me.
This is pure systems-level thinking. You use the stator windings of the main electric drive motor as the inductors for the boost circuit. While the car is stationary and charging, you use the motor and the inverter hardware you already paid for, and it's just sitting there as the charger electronics.
So you completely delete the dedicated onboard charger hardware?
Precisely. It is a zero-weight, zero-cost hardware solution. It's purely a new software control mode for the inverter. That is the kind of thinking that separates the winners from the losers in this game. It's not about adding more boxes. It's about making the existing boxes smarter.
Let's stay on the hardware for a moment and talk chassis manufacturing, gigacasting. Tesla obviously proved it works. Now it seems like everyone wants to do it. But I'm hearing a lot of pushback, especially from the insurance industry.
And rightfully so. Gigacasting is what I'd call a binary outcome manufacturing method. It's incredible. You cast the entire rear underbody of the car in a single shot from molten aluminum using these massive presses with 6,000 to 16,000 tons of clamping force.
And the win is huge for the factory?
It's a game changer for the bill of materials. It deletes 70, sometimes more than 70, stamped and welded parts and replaces them with one single part. But the pain side of the equation is what happens if a customer backs into a concrete bollard in a parking lot at 5 miles per hour and cracks that casting.
You can't just cut out the bad section and weld in a patch like you could with steel. The metallurgy doesn't work that way.
Nope. The material properties around the weld would be compromised. The car is, in many cases, totaled, written off by the insurance company for low-speed impact. That's not sustainable.
So what's the fix?
The strategic fix that we're seeing emerge for the 2026 model years is the sacrificial structural element. Engineers are now designing bolt-on aluminum crush cans or replaceable subframes that sit behind the plastic bumper but in front of the expensive gigacasting.
So you're anticipating the crash. You design it so that a $200 part sacrifices itself to save the $5,000 casting.
It is the only way to make the insurance premiums viable for these cars. If you, as the chief engineer, sign off on a gigacast chassis design without sacrificial nodes, you are effectively designing a disposable car, and the market won't stand for that.
All right, that's a great overview of the physical architecture. This is a good place to transition. Let's move into pillar 2. Virtualization and calibration. This is where we really start to address that time crunch. We need to cut validation time by 50% or more. Shift left is the mantra we all hear.
We hear it all the time.
And I feel like a lot of people say it without a concrete plan for how to actually execute it.
Well, shift left is a useless platitude without the tools and processes to support it. So let's get specific. Let's look at a critical bottleneck that the team at AVL identified: e-motor calibration.
Okay. Traditionally, this is just a long, tedious grind, right? You put the motor on a dynamometer, a dyno, and you meticulously map out every possible combination of torque and speed to find the efficiency sweet spot.
It's the grid-based approach. It's brute force. You set up a grid of, say, 2,000 operating points, and you have to go to every single point on that grid and measure voltage, current, temperature, vibration, everything. It takes 8 to 10 weeks to fully calibrate one motor.
And if the thermal team comes in halfway through and says, hey, we changed the cooling jacket design.
You start over.
Yeah.
The whole map is invalid. You just burned 10 weeks of expensive test cell time. And in an 18-month development cycle, you do not have 10 weeks to burn on a redo.
It's just not possible. So what's the new way?
The solution is active DOE, design of experiments, and it heavily utilizes AI. Instead of using a dumb, predefined grid, you use a neural network that models the motor's behavior in real time on the test bed.
Walk me through that. What does the AI actually see or do?
Okay, so imagine the motor's efficiency map is a landscape. Most of it is just a flat, boring plane. It's very linear, very predictable. A small change in torque gives a small, predictable change in efficiency. The old way tested that flat plane with the same density as the complex parts. The AI is smarter. It probes the system. It takes a few samples out on the plane, and its model quickly learns, okay, I get it, this area is flat and simple. But then as it explores, it finds a mountain or region where the torque ripple suddenly spikes, or the efficiency drops off a cliff due to magnetic saturation. The AI recognizes that this area is complex and nonlinear.
So it focuses its attention there.
It immediately concentrates all of its testing resources only on that mountain. It ignores the easy, boring stuff and hammers the hard, complex stuff. It creates what's called a space-filling design, where it optimizes the distribution of the measurement points to capture the most information.
And the results?
The data is clear. This approach cuts that calibration time from 8 weeks down to 4. It reduces the number of raw data points you need to collect by 30 to 50%, while actually increasing the accuracy of the model in the most critical, problematic areas.
That's a pure efficiency play. It's just faster and better. But let's talk about something more subjective, something harder to measure. Let's talk about steering. We're all moving towards steer-by-wire, or SBW, primarily to support Level 3 and Level 4 autonomy.
Right. You have to decouple the steering wheel from the road wheels. You need the car to be able to steer itself without the steering wheel spinning around in the cabin, and you need to be able to retract the wheel entirely in a future autonomous scenario.
But the trade-off is huge. If I'm driving a performance sedan, I want to feel the road through the wheel. I want to feel the texture of the pavement. I want to know when the front tires are starting to lose grip. If there's no mechanical link, all of that feedback has to be faked. It has to be simulated.
Synthesized is the polite engineering term. You use what's called a hand-wheel actuator, basically a powerful, precise motor on the steering column to generate forces that fight the driver's hands and simulate that road feel. But tuning this feel is an incredibly difficult, subjective art.
And you can't wait for the first physical prototype car to start that tuning process?
You'll be way too late. You have to tune that feel in a simulator early in the process. And this is where the VI grade report highlights a massive technical challenge. Latency.
The delay.
The delay. If I turn the physical steering wheel in the simulator and the visual display on the screen lags behind my input by even 20 or 30 milliseconds, my brain knows something is wrong. I'm going to get motion sickness.
It's that vestibular mismatch. Your inner ear says you're turning, but your eyes say you're not yet.
It's a disaster for effective engineering. To solve this, you need a XIL X-in-the-loop setup that is running on a hard real-time operating system.
Yeah.
We are not talking about Windows or standard Linux here. We're talking about something like Red Hawk Linux or a similar RTOS, a real-time operating system.
Why Red Hawk specifically? What makes a hard real-time OS different?
Because it can mathematically guarantee its interrupt response times. It guarantees that a task will execute within a specific window down to the microsecond. For haptics, for that steering feel to feel solid and rigid, you need a control loop time of less than 1 millisecond, 1,000 times a second. If the loop is too slow or inconsistent, the steering wheel feels spongy or notchy or just dead.
So the strategy you're recommending to the listener is you have to invest in a hybrid simulator, a real steering rack in one room, a real steering wheel in the driver cockpit, and you connect them with a high-fidelity digital twin of the car's dynamics model.
And that whole system has to be running on a hard, real-time kernel.
Yes.
And if you do that, you can achieve what we call virtual sign-off. You can have your chief dynamics engineer, your golden driver, sit in that simulator for a week and sign off on the steering calibration before the first physical car has even been welded together.
And that saves months and potentially millions in tooling changes down the line.
That's the ROI right there.
And this virtualization concept, it isn't just for small components like motors or steering racks. I was looking at the AVL source material, and they're doing this for massive industrial engines too.
Oh yeah, the virtual test bed, or VTB concept, is scaling up. They are applying this to 3-megawatt diesel engines for marine applications or power generation. To physically test one of those, you are burning thousands of liters of diesel fuel every single day.
And creating a ton of emissions, dealing with exhaust, heat.
It's a huge, dirty, expensive operation. By moving to a VTB, you replace that massive physical engine with a high-fidelity, real-time model of it running on the test bed's control computer. The physical dyno still thinks it's connected to a real engine. It's fighting against a big electric motor that is being controlled by the model, but there's no fuel being burned.
What's the bottom line impact of that?
They estimate a fuel cost saving of $600,000 per year for a single test bed. That goes straight to the bottom line. It completely changes the economics of engine development.
Okay, but let's play devil's advocate here for a second. We've simulated the motor map, we've virtually signed off on the steering feel, we've modeled the big diesel engine, but eventually you have to build the whole car and drive the thing to prove it can survive 150,000 miles of real-world abuse.
You're absolutely right, and that brings us perfectly to Pillar 3, the robotic and connected physical test. You cannot, today, perfectly simulate the long-term effect of a high-frequency vibration from a pothole on a suspension bushing. You need physical durability testing.
But the old way of doing this is just brutal. You're paying human test drivers to drive over the same cobblestone track for 8 hours a day, 5 days a week. It's a workers' comp claim just waiting to happen.
It's dangerous, it's mind-numbingly boring, it's expensive, and let's be honest, humans are terrible at it. We are inconsistent. If I, as the test engineer, tell you to hit a specific pothole at exactly 45 kilometers per hour at a specific angle of approach, you might do it correctly 4 out of 10 times.
So the obvious answer is to replace the inconsistent human with a consistent robot. And this is where AB Dynamics is the clear leader.
Right. And we're not just talking about a simple cruise control system. These are sophisticated drop-in robots that physically clamp onto the steering wheel. They have actuators that push the brake and accelerator pedals. They use a combination of GNSS and high-precision inertial motion units, IMUs, to track their position on the test track with 2-centimeter accuracy.
2 centimeters. I mean, that is tighter than a professional racing driver could hold a line lap after lap.
And they can do it for 24 hours straight, consistently, lap after lap, hour after hour. They don't get tired, they don't get distracted, and they don't stop for lunch. You can run lights-out durability testing 2147.
The productivity gain there is just obvious. But talk to me about the fleet management aspect. If I have 20 cars running around a proving ground at night with no drivers in them, that sounds like a demolition derby waiting to happen.
It would be, without the software layer. That's why systems like GTC Pro are so critical. They allow one single operator in a control tower to monitor and control the entire swarm of vehicles. And the robots themselves have multiple redundant integrated safety layers.
What does that mean?
It means they use ClearTrack LiDAR object detection. It's constantly scanning the path ahead. If a deer runs onto the track, or if another test vehicle breaks down in the middle of the high-speed oval, the robots in the following cars detect that obstruction and execute a controlled emergency stop.
And that's happening independent of the car's own ADAS or safety systems.
Completely independent. The robot has its own engine kill actuator. This is critical. Even if the car's own engine control unit, the ECU, freezes at full throttle, a software nightmare, the robot can physically kill the ignition and bring the vehicle to a safe stop. This is what gives OEMs the confidence to run things like the EPA drive cycle, the mandatory regulatory mileage accumulation, completely unmanned.
And we're talking about replacing a team of, 60 drivers working in 3 shifts with a team of maybe 5 operators and a fleet of robots.
The ROI, the payback period for these systems, is almost always less than 12 months. It's a financial no-brainer.
Okay, so we've automated the driver. Now, what about the equipment under the car in the lab? If we are doing lab-based durability testing, we have to talk about shaker rigs.
We do. And this is a classic consultant's dilemma that was covered really well in the material from Element. As an R&D director, you have 2 main tools in your toolbox for this: the MTS 329, which is a full road simulator, and the much simpler 4-post rig.
The MTS-329 is sort of the gold standard, isn't it? It's the really advanced one. It grabs the wheel hubs and can push, pull, twist, and turn them in every direction, all 6 degrees of freedom.
It offers the absolute highest fidelity. It can replicate the lateral forces of cornering, the longitudinal forces of braking and acceleration. It's an amazing piece of engineering.
I,
But it is astronomically expensive. It can take days to set up a new vehicle on it, and it has strict weight limits.
and with EVs and commercial trucks, weight is the new enemy. A fully loaded electric delivery van might just be too heavy for a standard 329 rig.
Exactly. And this is where the element analysis suggests a strategic step back. The much simpler four-post rig it just pushes the wheels up and down. It only provides vertical input. It offers no lateral or longitudinal force. But, and this is the key insight, vertical force accounts for about 90% of the fatigue damage to a suspension system and the body structure.
So the argument is, don't let the perfect be the enemy of the good.
That is the correct strategic engineering choice. A four-post rig is a fraction of the cost, it sets up in hours, and it can handle incredibly heavy trucks and buses. If you were trying to validate the structural integrity of a new battery pack mounting bracket, do you really need to simulate cornering forces? Probably not. The smart engineer, the effective manager, knows when to use the cheap tool to get 90% of the data 5 times faster. Don't overspec your test.
I think that's a great lesson. All right, let's move to the final stage of the process. We're in Pillar 4, the factory floor and end-of-line testing. The car is designed, it's validated, and now it's actually being built. But there's a massive communication gap that happens at the end of line, the EOL.
It's the Tower of Babel, but for engineering,
Yeah.
the factory. It runs on OT, or operational technology. The assembly line robots, the conveyors, the test equipment, they all speak industrial protocols like Profinet, EtherCAT, or Modbus. But the car, as we've established, runs on IT, information technology, protocols, CAN, FD, EIN, Automotive, Ethernet.
And they simply don't speak the same language.
Not at all. A Kachukia robot on the assembly line cannot natively send a command to a vehicle's battery management system, the BMS, to wake up and prepare for a high-voltage test. They're speaking German and Japanese to each other.
So you need a real-time translator.
You need a smart gateway. And this is where companies like HMS Networks provide solutions, like their ICSAT Mobilizer. This device is a protocol translator. It sits physically between the factory PLC and the car's diagnostic port. It takes an EtherCAT command from the factory network, translates it on the fly, and injects the correct CAN FD message into the car.
But it's not just a simple translation, is it? It's also about simulation. We've talked about this concept of RBS, or rest bus simulation. Why is that so critical on the factory floor?
Because modern electronic components are, well, they're needy, they're social. Let's say you are testing a battery pack as a sub-assembly before it's been installed in the final vehicle chassis.
Yeah.
You plug your EOL tester into it, the BMS wakes up, and the very first thing it does is listen for the engine control unit in the ABS module on the CN bus.
It's looking for its friends.
It's looking for its friends. And if it doesn't hear their regular heartbeat messages on the bus, it assumes the rest of the car is broken or is crashed, and it immediately goes into a safe limp mode or shuts down completely.
So you can't actually test it because it thinks it's all alone.
Exactly.
Hmm.
RBS, rest bus simulation, allows the gateway to fake the rest of the car. The gateway generates the required heartbeat messages for the engine and the ABS module, tricking the battery pack into thinking it's inside a fully functional vehicle. This allows you to run full load tests and diagnostics on a component level, which is much safer and more efficient.
Now, I have to raise a huge safety flag here. We are dealing with 800-volt batteries. If something goes wrong during that EOL test, say an internal short circuit inside the pack, that high voltage can travel back up the test cables.
And if those cables are connected directly to your factory network,
You've just fried the PLC, the gateway, maybe the entire server rack in the control room. You could take down the whole assembly line.
that is why galvanic isolation is an absolutely non-negotiable specification for any EOL equipment. You need gateways and interfaces that are rated for high voltage isolation, typically with internal barriers rated for 1,000 to 5,000 volts. Or, an even safer solution is to use fiber optic repeaters.
Because light doesn't conduct electricity.
Exactly. It creates the ultimate physical air gap. If the battery has a catastrophic electrical failure, the high voltage surge stops dead at the fiber transceiver. You might lose a $500 repeater, but you've saved the $5 million factory control system. It's cheap insurance.
Finally, let's close the loop on all of this. We've mentioned DevOps. We have all this rich data coming from the factory, from the robotic durability tests, from the virtual simulators. How do we stop it from just ending up in 100 different spreadsheets and 100 different silos?
This is the seamless model concept, and it's a huge strategic point from AVL. The way things are often done now is just broken. The design team builds a beautiful model in MATLAB Simulink. They throw it over the wall to the calibration team, who then has to rewrite parts of it to run on their Hill system. Then the factory team gets it and has to rewrite it again in a different language for the end-of-line tester.
You end up with 3 different versions of the truth. And if the design team finds a bug and updates the master model, the factory team might not get that update for 6 months.
It's a broken, leaky loop. The strategy for 2026 has to be a unified tool chain, something like AVL's Virtual Studio, that allows the very same model to be compiled and deployed to different targets. Use the exact same logic, the same source of truth, for your early-stage VL simulation, your hardware-in-the-loop rig, and the tester on the factory floor.
So if a bug is found on the factory floor during an EOL test, the data feeds directly back into that one master model, and the fix automatically propagates to everyone.
That is the infinite loot of DevOps, but applying to a hardware-centric product. It is the only sane way to manage the crushing complexity of a modern software-defined vehicle.
Wow. We have covered a massive amount of ground, from the geopolitical market split all the way down to the nitty-gritty of EtherCAT translation. Let's try to synthesize this. If I'm that R&D director, that chief engineer, listening to this deep dive, what is my Monday morning briefing to my team? What are the action items?
We can boil this entire report down to 4 clear strategic imperatives. This is your new playbook.
Okay, let's hear them.
Imperative number 1, consolidate the tool chain. You have to stop the Tower of Babel inside your own company. Force your teams to adopt and use seamless models that can travel from the first design sketch all the way to the factory floor. The efficiency gain from eliminating rework and translation errors is in the range of 30 to 40%.
Imperative 2.
Imperative number 2,
Yeah.
automate the dull and dangerous. Go look at your proving ground budget. If you are still spending millions of dollars on human drivers for mileage accumulation and durability testing, you are literally lighting money on fire. You must pivot to robotic drivers for 247 consistent and safe operations.
Imperative 3.
Imperative number 3, strategic virtualization. Don't just do simulation to check a box. Be smart about it. You must implement active DOE for calibration. If your teams are still grid testing motors, you are too slow. And you must leverage virtual sign-off for subjective, complex subsystems like steering to kill your dependency on late-stage physical prototypes.
And the final imperative.
Imperative number 4, secure the edge. Your factory is now part of your IT network. You have to bridge that OT-IT gap with smart gateways that support rest bus simulation and, most critically, high-voltage galvanic isolation. Do not expose your multi-million-dollar infrastructure to 800-volt spikes. It's malpractice.
That is the roadmap. It's not easy. None of this is easy, but the alternative is simply becoming irrelevant.
I'll leave you, our client, with one final provocative thought to chew on.
Go for it.
The auto industry loves to say we are building computers on wheels. It's a great soundbite. But most legacy OEMs are still organized, managed, and budgeted like they're building mechanical carriages with some chips added on. The biggest risk you face in 2026 isn't that your car will be too slow or your battery range too short. The risk is that you are still trying to solve software-defined problems with hardware-driven thinking.
You have to decide, culturally and organizationally. Are you a metal bender who buys software, or are you a tech company that happens to shape metal?
Exactly. And your survival absolutely depends on that answer.
This has been the Deep Dive Technical Strategy Report. To our client out there, good luck. You've got some work to do.
Break the silos. Go fast.
We'll see you in the next one.